You may have noticed in my previous video that I messed up a few times using the first derivative test, and the truth is, the reason why I messed up is because, I'll be honest, it's hard for me too. I get exhausted doing the first derivative test when I try to find critical points for a position function. And so basically, I remember this conversation I had with my pre-calc teacher when I was in 12th grade. And we were just, because he was a really good friend of mine. We were social after class, and I had him for 12th grade pre-calc. But when I was in 11th grade, I was in physics, and I hated physics. And he said, "Did you know that calculus makes physics a lot easier?" And I was like, "Really?" He's like, "Yeah. Think about it. Do you remember you had to memorize 3 formulas in physics?" I was like, "Yeah. Position, velocity, and acceleration." He's like, "Can you tell me those off the top of your head?" And I was like, "No." And he's like, "Well, the truth is you only need to know one, position. After that, right, you have a position function f of x. In other words, for f of x, it asks the question, at a certain x value, what is the y value? Pretty straightforward. But then when you want to calculate the velocity, everybody says, oh, I have to memorize the velocity formula. Fear not. You actually just need to know how to take the derivative of that function. Sorry, I forgot. I started the video and I don't have a pen. There we go. There we go. So there we go. So you have a position function, and then you can take its velocity function by just taking f prime of x. And he showed me, a blast from the past the year before, that there's a position function, there's a velocity function. It's like, the velocity function is the derivative of the position function. So velocity is the instantaneous rate of change. In other words, the change of position with respect to time. Notice that speed is measured in miles per hour. It's a change in position. But how fast was the change in position? So at a certain x value, what is the velocity at that particular point? And then finally, the last one is the acceleration function, f double prime of x. The f double prime of x is the derivative of f prime of x. So that's the derivative of the position function. But all you need to know is f of x is the position function, f prime of x is the velocity function, and f double prime of x is the acceleration function. Now, acceleration is the instantaneous change of velocity with respect to time. So in other words, if velocity is the change of position, acceleration is the change of velocity. So at a certain x value, what is the acceleration? Right? That should say acceleration. Sorry about that. At a certain x value, that's a typo. What is its acceleration? There you go. Okay. Now the truth is, we actually can use the acceleration in this situation. I didn't just go over this just to spew some nonsense, because may I present to you that your goal is to find the critical points. And how do you know if it's a local min or a local max? So we know that a critical point is attainable is a critical point can be found by setting f prime of x equal to 0 and solving for x. Simple as that. But may I present to you the second derivative test, the other method, the one that I find the most comfortable. So you set f prime of x equal to 0, and you solve for x. Well, the step 2 is that you take the second derivative and you plug in for f double prime of x. So you plug in the critical point that you got from here, and you plug that in to f double prime of x. Now, why do you do that? Because the main idea is it's like your crystal ball. The acceleration is like your crystal ball for the critical point. So if the velocity is 0, how do we calculate where it's going to go? So if f prime of x is 0, that means that a positive second derivative, a positive acceleration, will rise. Therefore, it's the characteristic of a local minimum. Goes from a lowest point back up. Now, if f double prime of x is negative, that means that this point right here is f prime of x equal to 0, and it will fall. So if f double prime of x is positive, local min. If f double prime of x is negative, local max. Simple as that. Okay? So the way another way I associate it is that song by Kesha, It's going down. I'm yelling timber, so I usually associate if it's going down, it's a local maximum. So if you want to sing that in your head, go for it. That's another way that I learned it. Another way to incorporate pop music into your life. So let's do some examples, but this time it's going to be the same 7 problems, but we're going to use the second derivative test, which is what I like. So without further ado, so what I like to do for this, if I'm going to use the second derivative test, what I like to do ahead of time is set up f prime of x and f double prime of x ahead of time. So f prime of x is, for problem number 1, x squared plus 4x plus 5. We're going to set that equal to 2x plus 4. And then the derivative of that, well, the derivative of 2x is just 2, and the derivative of 4 is just, well, 0. So in this case, it's a little bit different, but if you can master a quadratic, you can master everything. So that was a spoiler. And I look at this and I go, well, that's a spoiler. The first 4 are going to have spoilers. So without further ado, let's set f prime of x equal to 0. So step 1, set 2x plus 4 equal to 0 and solve for x. We're going to subtract 4 from both sides, getting us 2x is equal to negative 4. Now then, solve for x, divide both sides by 2, and x is equal to negative 2. So that x value is the x-coordinate of a critical point. And then what we would do normally is take f double prime of x, and that would be 2. And then we would normally plug in f double prime of whatever that x value is, but there's nothing to input it. But the idea is, okay, the second derivative is positive. So that means that it should be going up. So I like to put it in quotes, it's about to go up. So if it goes from a derivative of sloping 0 to going up, that's the characteristic of a local min. Okay. So looking at this graph, x squared plus 4x plus 5, and the critical point is located at x equals negative 2. That means that it's about to go up after f prime of x is equal to 0. The second derivative test proves it. Okay. Now let's take a look at the next one, x squared, negative x squared plus 18x plus 75, like we did last time. So what I like to do ahead of time is write down my f prime of x and write down my f double prime of x. I like to get them ready to unload. Negative x squared, the derivative of negative x squared would be negative 2x. And the derivative of positive 18x would be positive 18. And as big as it is, I'm not afraid of it. The derivative of negative 75 is just 0. So then I'm going to take the derivative of that. The derivative of negative 2x is going to be negative 2. And the derivative of positive 18 is going to be 0. So f double prime of x is equal to negative 2. Yet again, the acceleration is a constant. Okay. So then what I like to do is now step 1, well, after we set up the f prime of x, f double prime of x, is we set the derivative, set the velocity function equal to 0. Now we're going to subtract 18 from both sides. So then we get negative 2x is equal to negative 18. Okay, then we're going to divide both sides by negative 2, and that gets us, our critical point is located at x equals positive 9. So then what we would do is plug in f double prime of x, in this case, is equal to negative 2. But then, let's say it wasn't a constant function, we would plug in f double prime of 9, There's nothing to plug in for x, but I'm just showing this step anyway. F double prime of 9 would be -2. So I like to say it's going down. It is a local maximum. I know the words just fit through seamlessly. It's going down. So if it's going down after that critical point, that's the characteristic of a local max. And let's show it with the graph. All right, just to, yeah, at x equals 9, it goes down after it reaches its critical point. So that's the property of a maximum. Okay, let's delete that. There we go, move on. I don't need this paper anymore. All right, f of x is equal to 2x squared minus 8x plus 5. Find the x coordinate of the critical points and determine whether it's a local min or a local max. So let's do this. First things first, I want to get my derivative, my velocity function. So f prime of x in this case would be, the derivative of 2x squared would be 4x. The derivative of -8x would be -8. And then I would set my f double prime of x. So the derivative of 4x would be 4. And the derivative of -8 would be 0. So now that I've got my position, my velocity, my acceleration, let's find some critical points and determine, is that a local min or a local max? So let's set it up. F prime of x is equal to 4x minus 8, and we're going to set that equal to 0 because we want to figure out horizontal tangent lines. And let's solve for x. So how do I solve for x here? Well, I'm going to add 8 to both sides. So then I get 4x is equal to 8. Then I'm going to divide both sides of the equation by 4. So that means x is equal to 8 divided by 4, which is +2. So that's the x coordinate of my critical point. Now I'm going to use the second derivative test. So now that I know that f double prime of x is equal to 4, and just for the sake of doing the work, I'm going to plug in x equals 2. So there's nothing to plug in, so the function is still constant, so therefore, because the acceleration is positive, that tells me that once it reaches its critical point, it's gonna go up. It's going up. I'm yelling local minimum. Hopefully I don't get flagged for copyright infringement. Sorry, Kesha. But let's take a look at the graph. So we can tell that the critical point is located at x equals 2 because f prime of x is equal to 0 at this point. And the second derivative was positive, so that tells me once it reaches that critical point, when it goes to the right, it goes up. Those are the properties of a local minimum. Okay, now do number 4. Find the critical points for -2x squared minus 20x minus 46. Okay, so first things first. I need to know what my velocity and acceleration functions are. So let's figure out what f prime of x is, and let's figure out what f double prime of x is. Okay, f prime of x. So let's calculate the derivative of -2x squared. Okay, not too bad. That'd be -4x, and the derivative of -20x would be -20, and the derivative of -46 is 0. Then we could take the f double prime of x, that'd be -4. So my velocity can be achieved by plugging in -4x minus 20, and my acceleration can be just constant, -4. Now that I got that out of the way, let's figure out some horizontal tangent lines by setting f prime of x equal to 0. Let me just move my hand. Yeah, there we go. And setting that equal to 0. Okay, so now we're going to solve for x by adding 20 to both sides. Very happy. So then we get negative 4x is equal to positive 20. Then we're going to divide both sides of the equation by negative 4. So therefore, our critical point can be found at x equals negative 5. Now, after we figure out where our critical point is, let's figure out what f double prime of x is. In this case, it's just a constant negative 4. And just to show my work, I'm going to plug in x equals negative 5, even though there's nothing to plug in. Well, if f double prime of negative 5 is negative 4, well, what happens when the acceleration is negative at your critical point? If f double prime of negative 5 is negative, that means it's going down. It is a local maximum. Okay, just to plug that graph in. So because once it reaches a horizontal tangent and then it falls, that tells me that the acceleration at that critical point will be negative. So therefore, x equals negative 5 has a local maximum. Okay, now this is where the acceleration is really important. So now I'll throw this out. Okay, let's do 3 problems where now we actually have to plug in something for the acceleration function. Now we're in 3rd degree, 4th degree polynomials. So let's take a look at this. Find all the critical points and then determine whether those critical points are local min or local max. Okay, so first things first, what I'd like to do is set f prime of x and f double prime of x at the top. So I've got my position. What's the derivative of x cubed? That'd be 3x squared. And the derivative of negative 3x squared would be negative 6x. Okay. And then we're going to take the derivative of the f prime of x function. F double prime of x is equal to 6x. And the derivative of negative 6x would be negative 6. So now I'll actually have to plug in something for my critical point. Okay, so first things first. Now that I've gotten that part out of the way, here's where the real deal calculus kicks in. F prime of x is equal to 3x squared minus 6x is equal to 0. Okay? Then, I'm going to try to solve for x. Let's see if I can factor something. Can I factor something out of 3x squared and negative 6x? Well, 3 and 6 have a 3 in common. And x squared and x have an x in common. So I'm going to factor out the 3x. Okay? So 3x times x becomes 3x squared. And then 3x times negative 2 becomes 0. And then I break this up into 2 cases. So then I set, by the zero product principle, 3x is equal to 0, or x minus 2 is equal to 0. So either way, divide both sides by 3, x is still equal to 0. Or add 2 on both sides, and x is equal to 2. So now I've got 2 critical points. Not just 1, but 2. So looking back on the first derivative test, can you see why I like the second derivative test? I don't like to go before and after and at and analyze. Does it rise, stop, fall, or does it fall, stop, rise? I like the second derivative test. I'm not going to lie. I'm gonna impose my political views on you. I believe in the second derivative. I like the second derivative. Okay, so what we do now is we determine whether f double prime, so we've got f double prime of x is equal to 6x minus 6. But now we're going to plug in f double prime of 0 and f double prime of 2. Let's start out with 0. So if I plug in f double prime of 0, we're trying to figure out what the acceleration is at x equals 0. So that would be 6 times 0, which is 0, minus 6, which would be negative 6. Well, I don't care about the 6 per se, but I care about that negative. So at x equals 0, it's going down. It is a local maximum. My favorite song. I don't know. Might have a different favorite song after this video. Might listen to Green Day or something. All right, so then f double prime of 2, we're trying to figure out what the acceleration is at x equals 2, our other critical point. So even though the velocity is 0, it still has acceleration. 6 times 2 is 12, minus 6, that'd be positive 6. So what that tells me is that at x equals 2, it's going up So if it's going up, that is a local minimum. So according to our calculations, using the second derivative test, x equals 0 is a local max, and x equals 2 is a local min. Let's check it out with the graph. Boom. All right, I'm going to zoom in because I care about over here. X equals 0 is a local max, and x equals 2 is a local min, just like our calculations predicted. I love it. I love the second derivative. It's so much faster and easier to understand. I mean, I understand the first derivative test as well, but I made mistakes just on fatigue. I don't get fatigued using the second derivative test. In fact, I feel more energized. Okay, so let's take that off. We're going to do 2 more problems, and you see that we can do this using the second derivative test. Let's figure out all the critical points for f of x is equal to 2x cubed plus 3x squared minus 12x. Okay, so once we look at the problem, let's set up our f prime of x and our f double prime of x. So let's differentiate f of x with respect to x. The derivative of 2x to the third would be 6x squared. The derivative of positive 3x squared would be positive 6x. And the derivative of negative 12x would be negative 12. Then we can take f double prime of x by saying the derivative of 6x squared would be 12x. And the derivative of 6x would be positive 6. And the derivative of negative 12 would be 0. So now I've got my position, my velocity, and my acceleration. Let's solve f prime of x equal to 0. So if I set f prime of x, 6x squared plus 6x minus 12 equals 0, let's solve for x using our algebra. I can factor all 3 of these terms by 6. So I would be left with 6 times x squared would be 6x squared. 6 times positive 1x or positive x minus 2 is equal to 0. Then I factor this quadratic trinomial. What 2 numbers multiply to negative 2 and add to positive 1? Well, that combination has to be positive 2, negative 1. So x plus 2, x minus 1 equals 0. So now I've got my factored form in the... So now I will factor each piece. And now I've got x plus 2 is equal to 0 based on the zero product principle, or x minus 1 equals 0. Let me get my big old or. So let's solve for x. So x plus 2 is equal to 0, which tells me if I subtract 2 from both sides, I get x is equal to negative 2. That is one of my critical points. I'm going to put local min or local max right there. If I add 1 on both sides to the other equation, that tells me that my other critical point is located at x equals positive 1. So my other critical point is located at x equals 1. Now that I figured out that x equals negative 2 and x equals 1 have horizontal tangent lines, let's figure out what their acceleration are at these particular x values to determine whether it's going up or it's going down, or I need auto-tune. Okay, so then I do f double prime of x is equal to 12x plus 6. I'm going to plug in f double prime of negative 2. So now let's plug in f double prime of negative 2. 12 times negative 2 would be negative 24. And then negative 24 plus 6, it doesn't really do much damage to it. It's still going to be negative 18. So at x equals negative 2, it's going down. The acceleration is negative. That's all I care about. It's going down. So if it's going down, that means it's a local maximum. It achieved its highest point, and then it's about to go down. Let's check out f double prime of 1. So if f double prime of 1 can be calculated by 12 times 1, well, that's just 12. And then add 6 to that. That'd be positive 18. So if f double prime of 1 is positive 18, I don't care too much about the 18 part, but I do care about the positive part. At x equals 1, it's going up. So if it's going up, that means it's a local minimum. And let's check with the graph. So according to our calculations, f prime of x is equal to 0 at x equals negative 2, or x equals 1, but the acceleration at x equals negative 2 is negative. The acceleration at x equals 1 is positive, so therefore x equals negative 2 is a local max, and x equals 1 is a local min. So let's graph it. Oof. All right. Local max, local min. I love the second derivative test. I love it. It's poetry. All right, last one of the day using the second. Isn't this much easier than the first derivative test? I don't know, maybe it's just my enthusiasm. But anyway, last problem of the day. X to the fourth minus 2x squared. If that's our position function, well, let's figure out all the critical points. Let's figure out all those high and low points. All righty, so we figure out what our f prime of x is. And let's figure out what our f double prime of x is. So f prime of x is equal to, okay, the derivative of x to the fourth, that'd be 4x to the third. And the derivative of negative 2x squared would be negative 4x. Okay. Then our second derivative should be the derivative of 4x cubed. That'd be 12x squared minus 4. Okay. So now, first things first, we're going to set f prime of x equal to 0. All right, solve for x. Solve for all the values of x. You see all the years of Algebra 1, Algebra 2, Pre-Calc coming to help you all at once. We're going to factor out the 4x. 4x times, that'd be 4 times 1, x times x squared. So 4x times x squared would be 4x to the third. Let me make that a little bit clearer. There we go. All right, then 4x times what is negative 4x? That'd be negative 1 is equal to 0. Then we can break this up even further by saying, okay, this is 4x, but x squared minus 1, if you remember conjugates, right, the difference of two squares can be broken up into the square root of x squared and the square root of 1. So that'd be x plus 1, x minus 1 is equal to 0. So then I break this up into 3 cases. So either 4x is equal to 0, x plus 1 is equal to 0 or x minus 1 is equal to 0. So then let's take a look at the leftmost part. 4x is equal to 0. Well, 4 times what is 0? But even if I divide both sides by 4, 0 divided by 4 is equal to 0. So I'm going to leave space to say whether it's a local min or a local max. Then x plus 1 is equal to 0. I'm going to subtract 1 from both sides, leaving me with my other critical point, x equals negative 1. And then over here, I'm going to add 1 on both sides, and that gets me x equals positive 1. So I've got not 1, not 2, but 3 critical points, and I got to determine whether these are local mins or local maxes by using the second derivative test. So let me just draw a little divider over here. So recall that f double prime of x is equal to 12x squared minus 4, so I don't have to keep looking up. Okay. So first things first, let's do f double prime of 0. And then let's do f double prime of negative 1. And then let's do f double prime of 1. You know what? I'm going to stick with the positives first. So f double prime of 0, well, 12 times 0 squared, well, 0 squared is 0, so 12 times 0 would be 12. Oh, sorry, nope, quite, not that. 12 times 0 would be 0, and then minus 4. 0 minus 4 would be negative 4. So what does that mean? At x equals 0, it's going down. I need some auto-tune. But that means it's a local maximum. Because if it's about to go down, then it had a highest point and then it went down. All right, let's figure out f double prime of 1, because I want to do something positive first. Well, 12 times 1 squared, that'd be 12 times 1, or 12, minus 4 is equal to 8. So that tells me that at x equals 1, the acceleration is positive. So it's going up. So if you reach a critical point and then it's about to go up, those are the characteristics of a local minimum. And finally, we take the acceleration at x equals negative 1. All right, let me just put some dividers right here so we don't get confused. All right, so then we take negative 1 quantity squared. Well, negative 1 times negative 1 is positive 1. So this is quite similar. So that'd be 12 times 1, which is 12, minus 4. Yet again, the acceleration is positive 8. So what this tells me is that at x equals negative 1, it's going up. So if it reaches a horizontal tangent line and then it rises again, that is a local minimum. And no, it does not have to be rewritten in order, like negative 1, then 0, then 1. I just want to see the critical points and organize whether it's a local min or a local max. Okay? So let's look at this graph and see. I'm looking at the notebook right now. Let me just zoom in really quick. So according to our work, wow, it looks like a W. Our critical points are located at x equals negative 1, x equals 0, and x equals positive 1. X equals negative 1 and x equals positive 1 are local mins. X equals 0 is our local max. The second derivative is so useful. Hope you guys enjoyed this. And then I'm going to make some harder functions, but we're going to use some different derivative rules. And I hope you guys really appreciate the second derivative. I know you're going to end this video and you're going to go, oh, thank goodness, I know what the second derivative is during this shelter in progress. All right, have a good day.